Hello, everyone. Happy Saturday. Hope you're all having a really nice weekend so far. So in this video, I'm wrapping up my calc material. I wanted to go over some problems to talk about physics applications to calculus. Mainly, we are using integrals to solve physics problems. It's one of the more concrete applications of the definite integral. So for our first one, we're dealing with work. We want to find the work done by a force acting along an interval. So real quick, remember that force, just in a general sense, is used to find the work done. So just in general, work is equal to force times distance. F is a force in newtons, D is a distance in meters. So you can actually approach this as the area under the curve of a constant force. So for example, if we have a force being applied of 2 newtons, and we are applying this force along a distance of, let's say, 8 meters. So we have a rectangle. The area of a rectangle is base times height. We have a base of 8 meters. We have a height of 2 newtons. The area under the curve of this rectangle is 16, which also gives us force times distance. So we can say that the work done in this situation is 16 joules. So why do we even need calculus? So we need calculus because sometimes we're going to have a force that is not constant. So this is a really nice situation. The force is constant. It does not ever deviate from 2 newtons. The problem is in certain situations, you're going to have a force that varies as x. So as x changes, the amount of force being exerted by the system is also going to vary. It's going to increase or decrease like it does in this situation given right here. So in this case, we're still going to be finding the area under the curve, but it's not going to be quite as easy, nor is it going to be quite as nice. We're going to have an area that's not going to be rectangular. We're going to have an irregular area that we're going to use integration to find the area of. So that being said, work can also be found by integrating from A to B the force. I'm going to use capital F of F for the force, integrating our force function along a distance of dx. So x is our distance, dx is the differential with respect to distance. So we want to set up the integral like this. So the work is going to be equal to integral. We know we're going from 0 to 3. And our force function given is x times sine of the quantity pi over 4x. So now that we have it set up, that is half the battle. Half the battle is knowing what goes where and how to set up the integral properly. And then the other half of the battle is actually doing the integral and getting your answer. So if we didn't have this x out front, it would be a simple u substitution integral. But the fact that we have an x there complicates things a little bit. So we have an integral of one thing times something else. It's a product. So we want to approach this with integration by parts. So remember the key with integration by parts is being strategic in how you pick your u and your dv to start with. So for u, you want to pick u to be the function that gets simpler when you take the derivative. So if we picked sine, for example, the derivative of sine is cosine, and then the derivative of cosine is negative sine. The derivative of negative sine is negative cosine, and then the derivative of negative cosine is back where we started with sine. So you can tell that this one does not get simpler when you take the derivative. That being said, x would be a very excellent choice for you, because when you take the derivative of x, you get 1. When you take the derivative of 1, you get 0. It gets simpler when you take the derivative. So I'm going to have u be x. So that means dv is automatically going to be everything else. So dv is going to be sine of pi over x, no, pi times x over 4 dx. And remember that the formula for integration by parts is this. It's the integral of u dv is equal to uv minus the integral of v times du. So we have about half of the information we need. We still need a du, and we still need v. So du, the derivative of u with respect to x. Well, the derivative of x is 1, and if we multiply both sides by dx, we get du is equal to dx. And then finding v is a little trickier. So instead of taking the derivative of dv, we need to take the antiderivative of dv to get v. We need to work backwards. So this is a u substitution integral. We're going to have u be everything in parentheses. That's our inner function. So u, excuse me, u is pi times x over 4. If we take the derivative of that, we get pi over 4. And if we were doing the chain rule for derivatives, we would multiply everything by the derivative of the inner function. This is how the chain rule works for derivatives. But we're not doing derivatives, we're doing the opposite of derivatives. We're doing an antiderivative. So that means instead of multiplying by pi over 4, we're going to divide by pi over 4. And dividing by pi over 4 is the same as multiplying by 4 over pi. So we're going to multiply by 4 over pi. And the antiderivative of sine is negative cosine. So I'm going to put the negative out front and write cosine of our inner function. So there you have it. That is v. This is the antiderivative of dv. So now that we have everything, we're ready to plug everything in to the integration by parts formula. So we have u times v. U is x, and v is negative 4 over pi times the cosine pi over 4 times x. And we are evaluating from 0 to 3. And then we're going to subtract the integral of v times du. Integral from 0 to 3. V, which is this, negative 4 over pi times cosine pi x over 4 times du, which in this case is just dx. So we have some evaluation to do right here. We're going to do f of b minus f of a, f of 3 minus f of 0. And then we have one more thing to integrate. So for our next line, I'm going to evaluate. So we have x, so that's going to be 3, times negative 4 over pi, times cosine. If we plug in a 3 right here, this is going to be 3 pi over 4. So we have the cosine of 3 pi over 4, which is square root of 2 over 2. And then I'm going to subtract the same thing we get if we plug in 0. So if we plug in 0 for x, this whole thing is just going to become 0 because 0 times anything is 0. So f of b is this is f of 3. And f of 0, f of a is just 0. So we're subtracting f of a, we're subtracting 0. And then this is another u substitution integral. So we have this function to be u. du is going to be pi over 4. So then we're going to multiply both sides of the differential equation by 4 over pi, in addition to the 4 over pi that's already out there. So negative times a negative is going to be plus. And then we're going to have 4 over pi squared. Because we already have a 4 over pi, we're going to multiply by another 4 over pi we get from the substitution. And then the antiderivative of cosine is sine. So we are going to do sine of our inner function, pi over 4 times x, evaluated from 0 to 3. So we're in quadrant 1, if our angle is 3 pi over 4. And in quadrant 1, for this particular angle, sine and cosine are going to be the same. So cosine is root 2 over 2. Sine of 3 pi over 4 is also going to be root 2 over 2. So we can simplify things a little bit. We have, for this part, we're going to have negative 12 over 2. So that's going to be -6. We have -6 square root of 2 over pi. And then we can simplify this next part as well. This is going to be 16 over pi squared. And then we have sine of 3 pi over 4, which is square root of 2 over 2, minus sine of 0, which is just, conveniently enough, it's just 0. So that means our final answer, if we simplify, is going to be, this is going to be 8 square root of 2 over pi squared, minus 6 square root of 2 over pi. If we had just a pi instead of a pi square in the first fraction, we could combine them, but we're not going to worry about that. We're not going to trip over the semantics. This as an answer is perfectly okay. Okay, so that is the work done by a variable force, starting at 0 meters and then ending at 3 meters. Alrighty, right. So let's try another one. Let's try a bit of a different example. So let's say that we had a bag of sand originally weighing 144 pounds was lifted at a constant rate. As it rose, sand leaked out at a constant rate. The sand was half gone by the time the bag was lifted 18 feet. How much work was done lifting the sand this far? And then we want to neglect the weights of the bag and the lifting equipment. So I like to draw a picture whenever I'm being faced with a problem like this to help me understand the situation a little bit better. So we have a bag of sand on the ground, starting at a height of 0 meters. And then we are lifting the sandbag up to 18 feet. I guess we're starting at 0 feet and we're ending at 18 feet. I want to make sure the units are the same. Our bag is full of sand. And then we're ending at a height of 18 feet. So I don't know how it's being lifted. I'm assuming it's going to be some kind of a pulley. So we have a pulley lifting up the sandbag at a constant rate. But there's a hole in the bag, so sand is also leaking out at a constant rate. So I'm going to draw another instance of time, which makes the sandbag reach this height. So you know what? Actually, I'm going to make this be 18. So 18 feet is the point at which half of the sand has leaked out of the bag. So what else do we know? We know that we're starting at an initial weight of 144 pounds of sand in the bag. This occurs when we're at a height of 0 meters. And then the lifting starts, and then we start losing sand. It tells us that sand leaked out at a constant rate and that half of the sand was gone by the time we reach a height of 18 feet. So that means, I don't know why I put meters. I'm so used to meters, but I guess we are in feet this time. My apologies. So half of 144 is 72. So we know that the bag has a weight of 72 pounds when we reach a height of 18 feet. So the question is, how much work was done by lifting the sand this far? So just like last time, we need a force equation to integrate, and then we'll get the work. So as a quick recap from last time, the work done by a force is equal to definite integral from our starting point to our ending point of capital F of x. Our force function, dx. So we don't have the force function, and that's what we are going to devote our time to creating. So we know that the force is not it's not a constant force because sand is leaking out of the bag. So at the very beginning, our bag is completely full of sand. But when we reach this 18 feet mark, we only have half of the sand remaining. So that means that we are exerting half as much force as we did at the beginning. Half as much sand means we're exerting half as much force. So that means it is indeed a variable force. And we need to create an expression that will give us what that is. So first we need to come up with a model for how the force is changing. So the change in force can be modeled as a change in weight. Sorry, delta weight. This is the change in weight divided by the change in distance. This is the model we'll use to figure out how the force that the bag of sand is exerting on the lifting equipment. So I'm not going to get too far into it, but if we wanted to draw a free body diagram and diagram all the forces on this object, we know that we have a weight of mg aiming down below, but then we also have a tension force as a result of the lifting equipment pulling this up. So this is F sub T, this is our tension force. So as we lose sand, this right here, mg, decreases. So that means that the downward force overall is going to decrease as well. So that's what we're trying to model right now. So the change in weight over change in distance. So we know that we are starting at a weight of 144, and then we lose 72 pounds. We're losing weight, so that would be minus 72. And we are increasing a distance of 18 feet. So that means the change in weight over the change in distance on this interval is -4. So our force equation, capital F of x, is going to be the rate of change of the force, which is -4 times x, because that's how much weight we're losing per net unit of distance, -4x. And then we need to add the starting weight because this is initially how much force is being exerted. We're starting with a net downward force of 144, and we're losing this much per unit of distance. So this is our force equation. And now all we need to do is integrate it to get the work done on the interval. So work is going to be defined as the definite integral. We're going from 0 feet to 18 feet of -4x plus 144. This is our force equation. And then from here, it's pretty simple. Just take the antiderivative. The antiderivative of -4x is going to be -2x squared. And the antiderivative of 144 is just 144x. We're integrating from 0 to 18. So if we plug in 18 squared times -2 is -648. And then 18 times 144 is 2,592. And that is f of b, f of 18. So f of a is just f of 0, which is just conveniently enough, it's just 0, which is really nice. So ultimately, our answer is going to be -648 plus 2,592. So we get 1,944. 1,944. And this is how much work is being done, and work is measured in joules. Joules, it's kind of a measure of energy being released. So when we do work, we're releasing energy from the sandbag to other components in the system. So in this case, some of the energy is being transferred to the lifting equipment, some of it is being lost as heat to the surroundings. So joules is just a measure of the net change in the energy in the system as a whole or in individual parts of the system. So this is how many joules of work is being done by lifting the sandbag that's constantly losing weight. All right, maybe let's try one or two more. So let's try, let me find a good one. Okay. Now we're going to be dealing with something a little bit different. We're going to be dealing with a spring. So this one, I'm reading from a textbook. So I'm doing number 9 from my textbook. It tells us that it takes a force of 21,714 pounds to compress a coil spring assembly on a New York City Transit Authority subway car from a free height of 8 inches to a fully compressed height of 5 inches. So for the first part, it wants us to find the assembly's force constant. So the thing about springs is that every spring has a unique property called a spring constant, which is kind of a measure of the thickness of a spring. So I'm going to do my best to draw a spring. It's not going to be pretty, but this is what it looks like. So this is what we call the equilibrium position. If you leave the spring alone, don't stretch it, don't compress it, it's going to have this equilibrium position right here. So if you stretch it out and then you release it, it's going to go down and then it's going to go up. And then it's going to go down a little bit less than last time. And then it's going to go up a little bit less than last time. And it'll keep oscillating back and forth, back and forth, back and forth until it gets back to its equilibrium position. Same thing happens if you compress it and let it go. So the more you compress it, the longer it'll take for it to reach its equilibrium position. So like I was saying, every spring has something called a spring force constant, which is kind of a measure of the stiffness of a spring. So if you imagine a slinky, that toy that we all used to play with as kids, a slinky is not very stiff. You kind of release it, it doesn't go back and forth, it kind of just falls into place nicely. So we can say that a slinky doesn't have a very high spring force constant. Something like this, with a lot of gaps between the coils, this is going to have a very high spring force constant. It's going to be very stiff. So there's actually a way you can calculate the spring force constant. So it's a spring that's stiffer is going to have a higher spring force constant. So there's a formula. This is actually called Hooke's law. Robert Hooke was a famous scientist, and he discovered that the force exerted on a slinky, or not a slinky, just a spring, I should say, is equal to the spring force constant K times the compression distance. So for number 9, we're dealing with a force of 21,714 pounds. We don't know the constant, but we do know that our subway car assembly springs are being compressed from 8 inches to 3 inches. So the change in distance is 3 inches. So we just need to divide both sides of the equation by 3. So we have 21,714 divided by 3. We get 7,238. So that is the spring force constant for this problem. The next part is asking how much work does it take to compress the assembly the first ½ inch? Okay, so we already have our force equation, which is really nice. So force is equal to K times X. Our force equation, capital F of X, is equal to 7,238. And then we're not going to have X be 3. We're going to leave X as X. Because in the first theoretical situation, we compressed our spring assembly down from 8 inches to 5 inches. And we use that to calculate the spring force. But now we're doing something different. Now we're actually just compressing it down 1/2 inch. And we're trying to find the work. So instead of having X be 1/2 in this case, we're going to set it up like this. Whoops. We're going to set it up this way. We're going to have work equal to 0 to 1/2. So this is where the 1/2 comes into play. It's the upper bound of our integration because this is going to be the ending interval in which we're calculating work being done over a distance. So the x is variable, the distance is not. So that's why we leave x as x and we integrate from 0 to 1/2. So just like before, setting up the integral is the hard part. Now, once we've set it up, it's actually pretty easy to integrate this. So the antiderivative of 7,238x is going to be the same thing times x to the second power over 2. 7,238x squared over 2, going from 0 to 1/2. So if we plug in 1/2 for x, 1/2 squared is 1/4. So we have 7,238 over 2 times 1/4. So that's times 1/2 times 1/4, which is the same thing as times 1/8. And 1/4 times 1/2 is 1/8. So 7,238 divided by 8 is 904.75. And then if we plug in 0, the whole thing just becomes 0. So the total work it takes to compress the spring down by 1/2 inch is 904.75 joules. And then I wanted to see if there was another one. Yeah, I think we should do just one more. This one is different yet from the last 3. So suppose we have a fish tank with a base of 4 feet by 2 feet. And we have a height of 2 feet as well. And as always, I'll try my best to draw it, but no promises as to the quality of the drawing. So this is our fish tank. Geez, that does not look good at all. I think I can redo that part. There we go, that's somewhat better. So suppose we filled our fish tank up within 2 inches of the top. So if we have a height of 2 feet and a width of 2 feet and a length of 4 feet, our height is 2 times 12, that's 24 inches. That means we're only filling it up to 22 inches. We're filling it within 2 inches of the top, so the fluid height is 22 inches. So let's see. Excuse me 1 second. This is number 25. So we want to find the fluid force against each end of the tank. So the way this works is a single water molecule exerts a force. We call it a hydrostatic force in all directions. So a group of these water molecules are going to exert a net hydrostatic force as a body of water against the surroundings. So they're going to exert a net hydrostatic force against all 5 of the walls of the aquarium. There's nothing at the top, so that's why it's only 5 and not 6. We don't have a wall at the top. So there's a hydrostatic force being exerted on all 5 of the walls. And we want to find the force being exerted on just one of them. So we need special formulas to help us figure out what that would be. So total fluid force actually depends on something called fluid pressure. And fluid pressure depends on the weight density of whatever compound we're dealing with. So every fluid has a really specific weight density. In the case of water, water has a weight density of 62.4 pounds per cubic foot. No, sorry, I was right, pounds per cubic foot. I shouldn't doubt myself. 62.4 pounds per cubic foot. This is the fluid density or the weight density of water. So now that we have that, we need to calculate the fluid pressure. So fluid pressure, there's a lot of writing here. So fluid pressure is going to be the weight density times distance. In this case, it's going to be not just a distance, but an area. So we're applying the fluid pressure on an area. So fluid pressure depends on the weight density. So something with a higher density is going to exert more pressure. And it also depends on the area. So if we're exerting a fluid force on a small area, the pressure is going to be more concentrated than it would on a larger area. So fluid pressure is going to be the weight density times whatever the area is of our concentration. So I'm just going to call that A. A is the area on which the pressure is being applied. So we need to come up with an expression to give us a sense of what A should be. So looking at our fish tank, I'm just going to deal with this particular side right here. So imagine if we have a small horizontal strip at the bottom with a negligible height. This is it's delta x if we can measure it. So for example, if we're going to a height of like 2 inches, delta x would be 2. But imagine we're taking it so small that it becomes negligible. So it transforms from a delta x to a dx. So you can think of dx as kind of the limit as x approaches 0, as delta x approaches 0. So the area of a thin horizontal strip is going to be 2 times dx. So fluid pressure can be written like this. For a small strip, it's going to be the fluid density times 2 dx. So this is what it is for a small horizontal strip. To figure out what it's going to be for the entire tank, we're actually going to integrate from the bottom of the tank to the top of the tank. But we need some information before we're even ready to do that. We need to compare the water depth to the other units that we have to make sure that everything play nicely, to make sure we have the same units for everything. So for example, weight density has feet involved. So we want to make sure that our height is also in feet. So we know that we're dealing with a height of 22 inches. 22 inches. We're going to figure out how many feet that is. So we know that there are 12 inches in a foot. Inches cancel with inches, we're left with feet. So 22 inches is equal to 22 over 12, or 11 over 6 feet. So this is the height of the water in the tank. So now that we have that, we're ready to calculate the total fluid force. So like I said before, to figure that out, we need to integrate this small strip of area from 0 all the way up to our maximum height to tell us the total fluid force acting on this entire wall, the entire panel on the side of the fish tank. So total fluid force, I'm going to use capital F of X for the force. You know what? Actually, no. That might get confusing. So I'm just going to write it out and not be lazy. So the fluid force being exerted by the water on the side of the fish tank is the definite integral from 0 inches. No, I meant to make that feet. This is 11 over 6 feet, not 11 over 6 inches. Sorry, I need to get it together. So the fluid force is going to be the integral going from 0 feet to 11 over 6 feet of our fluid pressure equation. So if you integrate fluid pressure, you get fluid force. So we have 62.4 times 2 dx. So 62.4 times 2 is going to be 124.8. And you can move that right outside. And I forgot the x. You should never forget the x. So we're left with the integral from 0 feet to 11 over 6 feet of x dx. So the antiderivative of x is just 1/2 x squared. One half x squared being evaluated from 0 to 11 over 6. So 124.8 times 1/2 is 62.4. And then if we plug in 11.6 into x squared, we get 121 over 36. And if we plug in 0, we just get 0. So let's figure out what this is going to be. So we have 121 times 62.4 divided by 36, which gives us an answer of 207.73 repeating. .73 repeating. And fluid force is measured in newtons. So this is how much force is being exerted on the rightmost wall of our aquarium. All right, guys, hope you found this useful, and I'll see you in the next video. See you later.